Once air is within the alveoli of the lungs, what promotes the diffusion of oxygen from that air into the bloodstream? The pressure behind that oxygen is one primary driving force. Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the partial pressure of each gas. The movement of oxygen into the bloodstream is dependent on the partial pressure of oxygen within the air in the alveoli. Gases are molecules that exert pressure on surfaces. A higher pressure of a particular gas means that there are more of those gas molecules present in that mixture. Earth's atmosphere is a mixture of gases. The two most common gases are nitrogen and oxygen. Nitrogen composes 78% of the gas in the atmosphere, while oxygen composes 20.9%. As one moves up in elevation or altitude, the percentage of these gases in the atmosphere remains the same. There's just fewer gas molecules overall and less pressure and less atmospheric pressure. This means that there is less partial pressure of oxygen in that air and less oxygen being driven into the blood by diffusion. So, for example, let's say we want to find the partial pressure of oxygen, or the PO2, if the total atmospheric pressure is 500 millimeters of mercury at 10,000 feet elevation. In this example, we are only concerned with two numbers, the total atmospheric pressure, which is 500 millimeters of mercury, and the percentage of oxygen in the atmosphere. The 10,000 feet elevation is just extra information in this particular question, but be aware that you may have to look up the total atmospheric pressure if given a specific elevation for this type of problem. The first step, now that we have the important pieces of information, is that we must convert the percentage of oxygen into a decimal. Percentages are just numbers between 1 and 0, so 20.9% becomes 0.209 by moving the decimal point to the left 2 places. Another way to find this is to take 20.9 and divide it by 100. Next, we multiply the total atmospheric pressure by 0.209 to find the partial pressure of oxygen at that altitude. In this case, it would be 500 multiplied by 0.209, which after rounding gives us a partial pressure of oxygen of 105 millimeters of mercury. If we compared this to sea level or 0 feet elevation, the total atmospheric pressure is typically 760 millimeters of mercury at sea level. And multiplying that by 0.209 gives us about 159 millimeters of mercury for the partial pressure of oxygen. So we can see that moving to an altitude of 10,000 feet drops or decreases the partial pressure of oxygen by about 55 millimeters of mercury. This means that there's less pressure and less diffusion force behind this oxygen, so less oxygen diffuses into the bloodstream at higher altitudes. Of course, capillary blood flow to the alveoli must also match the amount of air entering the alveoli in order for the most efficient gas exchange to take place. This match between ventilation of air in the alveoli and the blood flow in the alveolar capillaries is referred to as ventilation-perfusion coupling. If airflow or ventilation to the alveoli decreases, blood flow to the alveolar capillaries also decreases. So there is a direct correlation between ventilation and blood flow. If airflow or ventilation to the alveoli increases, blood flow to the alveolar capillaries will also increase.